Amy Trang, and I am a volunteer with APACAF. It's a nonprofit, volunteer-based organization that supports youth development and leadership programs. And one of the programs that we support is STEM, Scouting Center for STEM, SSSTEM for short. Today we have a lovely guest speaker from Boston. Her name is Dr. Jane Liu. And before I introduce Dr. Liu, I'd also like to acknowledge that SBTN and Wegmans helped sponsor the program today. So they provided some snacks and prizes. And for anybody here who's under 18, raise your hand. All right. Well, for those who are under 18, listen very carefully to what Dr. Liu has to say today, because at the end, we're going to ask you some questions, and if you get it correct, you might get nice prizes, all right? And they're very fun prizes that you can take away and be excited about, okay? All right? Yes. I can't hear you. All right. Okay, so without further ado, the other thing I'd like to remind everybody is if you have a cell phone, who has a cell phone here? Please turn off your cell phones. Anybody have an iPad or a tablet? All right, turn it off. Don't play with it. Full attention, okay? All right, so Dr. Jane Liu was born in South Vietnam in 1963. And because her father had been an interpreter for the U.S. Army during the Vietnam War, her family had to leave Vietnam in 1975 and settled in the United States. Who knows what happened in 1975? What happened? Vietnam War came to an end. What else happened?
The yellow flag of Vietnam came down and the red communist flag was replaced.
That is what happened, sadly enough. And how many people here fled to the United States after that? How many people's families fled to the United States after that? That's right. And that's the reason why most of us are here today, right? So Dr. Liu is no different. Her family settled in the United States, and in 1980, she was awarded a scholarship. Do you know what a scholarship is?
Yes.
What's a scholarship? Something that you earn because what? What have you done to earn it? You did a project? Yes. Anything else? Anybody want to add? Yes. You did something good. You studied very hard. How many people here are studying very hard in school? I hope so. All right. Well, Dr. Liu studied very hard, and she studied physics. Do you know what physics is? What's physics? It has a lot to do with science. That's right. And she studied it at Stanford University. Where's Stanford University? Anybody?
I don't know.
You don't know? California. California is on the other side of the country, right? So you have to drive there or sit in a plane? If you drove, you would probably go for a week. But the fastest way to get there would be by airplane. Correct. And after completing her undergraduate studies, Dr. Liu was accepted to the doctoral program in planetary astronomy at the Massachusetts Institute of Technology, also known as MIT. Anybody heard of MIT? No. No. Anybody here heard of MIT? Parents, you can talk to, don't worry. Anybody? Yes. MIT, you want to tell us what MIT is? It's the top school for technology and science. That's correct. Anybody here want to go to MIT now? If you get a scholarship, right? Yes. Okay, so in 1992, Dr. Liu and her former thesis advisor, David Jewett, unexpectedly discovered the first Kuiper belt objects, and I'm probably saying this wrong, but Dr. Liu is going to correct me later, which paved the way for discovery of more Kuiper belt objects and led to better understanding of planet formation. Does anybody know what a Kuiper belt might be? What about planets? Has anybody heard of planets? Go ahead, tell me. Yeah. Yeah. Great forms of mass in a ball.
About it later.
Yeah, she's going to talk about it. And is it on the ground? Can we see it? Where was it?
We live on it.
Yeah, we live on it, outer space. That's right. She's going to talk more about it, okay? And last year, they both were awarded the Shaw Prize in Astronomy and the Kavli Prize in Astrophysics with Michael Brown for their pioneering research. On March 28, 2013, Jane and other 2012 Kavli Prize laureates were recognized by President Obama in the Oval Office for their landmark contributions. Until now, Jane is the only female Shaw Prize laureate. In 1991, she won the Annie J. Cannon Award in Astronomy, and asteroid 5430 Lu is named in her honor. So, can everybody please welcome Dr. Jane Lu?
Okay, so, can you guys hear me? So I'll try to make this not boring. It's going to be a story. It has a happy ending, too. Okay. So not too long ago, astronomers thought they knew everything in the solar system. There were the planets, the satellites, the asteroids, the comets. We thought we knew everything in the solar system. It was our backyard. We knew everything. We thought the inventory was complete. Everything was known. So in fact, if you talk to the average astronomer, this person would say, why bother the solar system at all? Everything is known. It's so boring. But then in 1992, discovery of a new population of objects beyond Neptune called the Kuiper Belt changed this view upside down. And it showed us that we're really, really far from understanding our own solar system. So my talk today is about the history of how the Kuiper Belt came to be. The standard theory of how planets form is that everything formed from a molecular cloud. Something like this. It's just a big cloud of dust and gas. And if this cloud gets too big, too heavy, it collapses. And when it collapses, it forms, looks something like this, a disk with a bulge in the middle. So this is going to become the sun later on. And then this disk called the solar nebula is also contain a lot of dust and gas. And that's where everything in the solar system comes from. All the planets, all the comets will come with the solar nebula. And we know a lot about the solar nebula because we have seen other solar nebula in around other stars, like this one. So this is a young planetary system that we have imaged in the Orion Nebula. So you can see it looks a lot like this. There's a bulge in the middle, that's a young star, and there's a disk around it. That's the nebula. Okay? And so this thing is just a young planetary system. Eventually, it will make planets, comets, asteroids, everything. Okay, so you have a nebula. So then how do you go from the nebula to planets? First, the dust in the nebula have to collapse into a mid-plane in the middle. And then, so then you have a thin disk of dust. And somehow the dust have to grow into big planets. And how does that happen? We don't quite know how dust goes into, we don't know how dust collide and get bigger. Maybe they form in clumps, maybe dust grains just collide and stick together. That part we're not so sure about. So we just skip to the next step that we know something about. When things start becoming when things go to be about 1 kilometer in size. We call these things planetesimals. They're about 1 kilometer, and the word planetesimal just literally means building blocks of planets, okay? So my story will take it from there. So let's say somehow the dust grain become 1 kilometer size planetesimals. And the 1 kilometer size is important because when things reach that size, they start attracting each other by gravity. You can imagine the bigger ones will attract more things than the smaller ones. So what ends up is a few large bodies start attracting more and more and more other bodies to them compared to the smaller guys. So a few big ones will just grow much, much faster. And what we call it results in something we call runaway growth, where a few large bodies keep growing and growing faster than everything else. And they grow just by attracting other bodies. 2 bodies collide, they stick together, and they grow bigger. Okay, so then you have these. So at the end of that, you have a few large bodies, which now we call planetary embryos, and they're about 1,000 kilometers across, about the size of, say, Mars or so. And at this stage, the gas goes away. With the gas gone, the orbits of these things start becoming a bit more chaotic. They start colliding with each other more, and so that allows the planetary embryo to collide with each other. They stick together, and they grow even bigger, and that's how we get planets. So that's basically how we think planets form in the solar system. As early as about 1949, an Irish scientist named Edgeworth, well, he noticed, well, okay, our planet seemed to stop at Neptune or Pluto, but this solar nebula, it's unlikely that it has a sharp edge at the distance of Neptune or Pluto. So he reasoned, well, since it's unlikely that the solar nebula would have a sharp edge, maybe there are things beyond Neptune and Pluto that we didn't know about. Okay, so that was just an idea. And this guy, Kuiper, in 1951, he brought back the idea again. And so their reasoning is, if there are things still beyond Neptune or Pluto, they wouldn't be very big. They wouldn't be planet-sized, because remember, you need collisions for things to go big. And if it takes a long time for something to orbit around the sun, the time scale, how long it takes for things to go bigger, is very, very long. So if things exist beyond Neptune and Pluto, they just don't have enough time to grow very big. So for that reason, they probably stay small, about maybe comet size maybe. And so maybe if they're correct, there would be this whole population of small things beyond Neptune. Okay. But this is just, basically for both of these guys, they're just speculation. They're lucky guesses. They don't have any theory. They don't have any calculation to back up their claim. It's just an idea if they have. So nobody paid much attention. So this is one thing you guys should remember. If you're going to make a theory, you should do some calculation, and you have to do predictions. That's really important. If you don't predict anything, then your theory is useless, and after a while, people just forget about your theory. These guys didn't make any prediction. They just made up some guesses, and they say, oh, maybe it happened, maybe it didn't happen. So nobody paid much attention. Once in a while, people would bring back this idea in connection with one other problem. And that's the problem is, that problem, where do the planets come, where do the comets come from? Okay, now I'll talk a little bit about comets. Comets are small, icy things orbiting around the sun, and we recognize them by the fact that they have this big cloud around them called the coma. It has a tail. This coma, this big bright cloud around the middle, which is called the nucleus. The coma appears when a comet comes close enough to the sun, and it starts evaporating. And when because the ices on the comets evaporate, producing the coma. So inside the coma is gas molecules and dust particles come off because the gas molecules eject them when they escape from the nucleus. When the comet is far away from the sun, there's no evaporation going on, so what you see is just the comet nucleus, that thing over there. Okay. So the presence of a coma tells you one important thing, that the comet is made of ice. And if it still contains so much ice, that means that most of its life, it must be somewhere cold for the ice to remain frozen. It also tells you that the comet is constantly shrinking. It's constantly losing mass, because when it comes near the sun, the ice evaporates and flies off into space. So the comet is constantly shrinking. A comet like Comet Halley, about 10 kilometers across, would completely shrink to nothing in about 1,000 years. So that's not very long. Besides shrinking, comets also are under the influence of the planets. So often sometimes they plunge into the sun, sometimes they just escape from the solar system, sometimes they plunge into other planets. Like here, this is Jupiter. This is Comet Shoemaker-Levy 9 hitting Jupiter, making these spots. Okay? So given that an average comet comes to an end either by shrinking to nothing because it's losing mass, or plunging into a planet, so why do we see so many comets? The solar system is 4.5 billion years old, so why do we see so many comets? So the answer must be, there must be a reservoir of comets somewhere, constantly bringing new comets near to the sun where we can see them. So, but nobody knew where this reservoir of comets was. And since they didn't know, they were hoping maybe this idea of this trans-Neptunian comet belt, that might be the solution. But that's just a hope. Nobody could prove it. Okay. In 1987, I was just starting graduate school at MIT, and this guy, Dave Jewett, is my advisor at the time, and he told me about a question he had. Well, his question was, why was the outer solar system so empty? The inner solar system, which is from the sun out to Jupiter, this area here, is pretty full. You have the terrestrial planets, Earth, Mercury, Venus. You have another asteroid belt as shown here. But beyond Jupiter, from here out, there's not much, right? You have the three giant planets, and then you have this optional planet, Pluto. And so he just thought that it was pretty peculiar that this region is so full of stuff, and this region has very so little. So as he saw it, there were two possibilities. Maybe this region was really empty because the giant planets, they're so good at ejecting anything that came nearby, so maybe they just ejected everything away, clearing out the entire outer solar system. That's one possibility. The other possibility is that maybe there were things in the outer solar system, but they were too faint for people to see. Things in the solar system become faint very quickly. We see solar system bodies like comets and asteroids and planets because they reflect sunlight. If you take an object at Earth's distance, 1 astronomical unit, you move it 10 times further away, 10 astronomical units. It doesn't become 10 times fainter. It doesn't become 100 times fainter. It becomes 10,000 times fainter. So given the fact that solar system bodies become faint so quickly, so maybe there are lots of things beyond the planets that we did not know about. So that was the other possibility. Okay.
Hold on. We got a little commercial break because we're going to make sure that you can better hear Dr. Liu, and so we're going to put a cordless microphone as she explains the very intricate details of the new solar system. So far, has anybody been listening?
Does this work?
Okay.
It does. Okay. Okay, so as I was saying, so Dave Jewett, he was wondering why the outer solar system was so empty, and he came to the conclusion maybe it was empty, maybe it wasn't, and we just didn't see the other stuff. So let's see. So that was the way things were. We didn't know which was which. So in 1987, I had just started graduate school, and so I went to look for, I was looking for a project to do, and I talked to Dave, and Dave told me about this problem. I said, okay, that sounds good. And he said, so let's go look for things in the outer solar system. And I said, fine. So what the question was, how are we going to do it? At first, we thought the best way to do it would be by something called occultation. Occultation is when a solar system body goes in front of a star, and just for 1 second or so, it just blocks out the light from the star. And then it goes by, and then the star is bright again. So if you were to monitor, so if you look at a bunch of stars, and you monitor it, so these stars here, these are a bunch of brightness of stars occulted by asteroids, right? So here is just a star, you monitor the brightness, it's just the same brightness, and over here, there's a little dip because the asteroid was in front. Then after the asteroid has gone by, the star becomes bright again. Same with here, and same here. So these are the asteroids have been blocked by an asteroid, we call occultation. So we thought, okay, maybe we can use this technique and find things in the outer solar system. We'll just look at a bunch of stars and to see if they dim. But then the whippoorwills, this bird of Arizona, put an end to our idea. We were observing in Kitt Peak, Arizona at the time. And so we noticed that we heard a lot of bird songs. Let's let you hear that. So while we were observing, we heard this a lot. Stop. And so these birds are nocturnal, so they're very vocal at night. And so we made a phone call to the Audubon Society, and they basically told us it wasn't going to work. Because if there were real occultation, there would be too rare, too short, and too similar by occultation by birds. So that's the end of that idea. So we had to come up with a new plan. So our next idea is, well, we just maybe photograph the sky and see if we can see anything with a telescope. And we would do it two ways. First, we would use photographic plates, and then we would use CCD. First, the photographic plates. Photographic plates are just glasses, big pieces of glass with a thin film, which is sensitive to light. It's just like film, it's like negative. You put one of these glass plates in a telescope, you expose it, and then it takes a picture of the sky. And then you develop it, and you get a picture, just like negative. But the main thing about it is really, really big. And so we'll use that. We will also CCDs. These are the detector you see inside your camera, the CCD cameras that you use to take pictures with. So you can see they're pretty small compared to a photographic plates. So the plates will let us photograph big chunks of the sky. The CCD will let us photograph a small chunk of the sky, but we can see more faint things. And then we would recognize things that are far away by how fast they move. An asteroid, which is nearby, would move very fast. If a Kuiper belt object exists, it would move very slowly, and that's how we recognize what is what. Here's a picture to let you compare CCDs and photographic plates. This picture is a picture of M31, the Andromeda Galaxy. Okay? You can see the whole galaxy is captured in the picture. So it gives you an idea how big a photographic plate is. So this is what astronomers used to use before they had electronic detectors. This picture is the same galaxy, also the Andromeda Galaxy, but only a very, very small area of it, and it was taken with a CCD. So you can compare this, and you can see the difference. This is huge. The picture is enormous, but you don't get much resolution. You can't see the individual stars. But with a CCD, you can see the individual stars. So you get an idea of scale. This thing is about 1,000 times smaller than a plate, but it's about 100 times more sensitive. So this picture is basically, this is a computer room back from 1891. This is the plate room from Harvard College Observatory with a bunch of women looking at photographic plates. So this is what you have to do to analyze photographic plates before computers are along. You just sit there and you stare at a photographic plate and you look at every single dot on the plate. Is this one? Let's see. Well, now CCDs have become very big. This is the largest CCD in the world. It has 1.4 billion pixels. In contrast, this little red dot is the size of our original CCD. So at the time, the idea to use such a tiny, tiny camera to search a big chunk of the sky was a pretty crazy idea. Now it's easy because you have these enormous CCDs. What they really are is a mosaic of little smaller CCDs just stuck together. For example, like this. This is a picture of the moon, and it was taken by 8 CCDs stuck together. It's an array of CCDs. So this is how astronomers make bigger and bigger CCDs. They get little ones and they just stick them next to each other. So that's how people do it now. But back then, we only had one tiny little CCD. So yeah, so the idea, what we were doing at the idea was kind of crazy. Whether by photographic plates or CCD, the way you look for solar system bodies is the same. You take several pictures of the same piece of the sky and you compare them. Galaxies and stars, they don't move, so they stay fixed, but solar system bodies move. So if you take a bunch of pictures and you see something move from picture to picture, that's a solar system body. For example, with photographic plates, this is the 2 photographic plates that were used to discover Pluto. And Pluto is pointed by the 2 arrows. So as you can imagine, working with plates was painful. You have to look at every single dot, to see if anything moved at all. But so after we used one observing run with photographic plate, it was so painful we decided we would never use photographic plates again. Then instead we would use CCDs. So this shows you how you can find moving object with CCDs. You take a few images with a CCD, and then with a computer, you can display them. You can blink them one after another, so you can see the object moving very easily. Okay. Does that make sense? You just compare a sequence of images. If you see something moving, that's a solar system object. Okay. So these images are the images of a Kuiper belt object, 1999 KR16, and this is how we found it. We just take a sequence of images, and then we compare them on the computer. So we started our work in 1987. In 1988, Dave moved to the University of Hawaii, and I followed him. So now we get to observe at Mauna Kea Observatory. It's on the summit of the mountain Mauna Kea. It's in a volcano in Hawaii. It's in the middle of the ocean. It's very high. And being in the middle of the ocean and being very high made it a very, very good place to make observations. And this is a telescope that we use most of the time. This is a University of Hawaii 2.2-meter telescope on Mauna Kea. For those who think that life in Hawaii is mostly going to the beach, this is a much more accurate picture of life on Mauna Kea. As I mentioned, Mauna Kea is a mountain on Hawaii. It's very high. The summit is at 14,000 feet. Now, being high up and being in the middle of the ocean makes the atmosphere on Mauna Kea very stable, very dry. So that's why it's a really good place to make observation. But it's kind of miserable for people to be up there. Being so high up, the oxygen level at the top is about 60% of the oxygen level at sea level. So at the top, there's not enough oxygen to breathe, so you just feel tired all the time. Besides that, it's so dry that you're constantly being dehydrated. Okay? And on top of all that, being dehydrated, being cold, and not having enough oxygen to breathe, there's a lot of sitting. You sit in the computer control room and you wait. Sometimes it snows, sometimes it rains, and you just have to sit there and wait. And sometimes the work is just so boring that the telescope operator just goes to sleep in the middle of the night. So that's what observing is. So here's some more pictures of us in the telescope control room. Our search was not popular. People who control telescope time and funding agencies, they did not look very favorably upon searches for things that were not predicted by any theory. Remember, there was Kuiper and Edgeworth mentioned something about the trans-Neptunian comet belt, but there was no prediction. And if you have no prediction, then it's a useless theory. So there was no prediction. So people said, basically, you're just wasting your time. So we got telescope time mostly by stealing from ourselves. We would write proposals. We would get telescope time to do other things. And then we would steal that time from ourselves to do this search. So there were lots of nights sitting in this control room. Okay. And then finally, after 5 years in 1992, we had a big CCD. It became available on the telescope. And the first time we used this big CCD, we were able to find something right away. These are the discovery images of the first Kuiper belt object, 1992 QB1. And the images show you how it moved from frame to frame. We just took 4 images of the same piece of the sky, and then we would just compare them to see if anything moved. And you can see clearly that this object moved from here at 2056. It was here. About half an hour later, it's here. Then at 23:00, it's here, and so on. Okay? So these are the discovery images of 1992 QB1. So the way it happened was we had taken the first 2 images, and I was doing something, and Dave was blinking these images, and I didn't like doing that because with 2 images, it's very easy to have false alarm. You know, there might be fake things and that look like moving things, but they were not real. So Dave was blinking the 2 images, and he saw something right away. He noticed that there was this thing moving. It was moving the right direction, westward and south. It was moving very slowly, so consistent with something far away, and it was very faint. It was so faint that we knew that nobody had seen this before. It was pretty clear that it wasn't a fake object. It was very real, but it was unlikely anyone had seen it before. So he thought, oh, this looks pretty interesting. And then the 3rd image came out, and the object was still there. It was still moving in the right direction, still the same brightness. So that looked pretty hopeful. And then by the time the 4th image came out, exact same thing, same brightness, same speed, same object. It kept moving in a straight line. So by then, after the 4th image, we knew that we had found the first Kuiper belt object. So we were able to calculate. Oh, so here's an announcement after we made our discovery. From how fast it was moving, we could calculate how far away it was. This was beyond, so we knew that it was beyond Neptune, the most distant solar system object ever seen, the faintest by far. And from how bright it was, we could calculate how big it was. It was about 250 kilometers. So we knew we had found a 250-kilometer object beyond Neptune, about 41 AU. But not everybody believed our discovery. This guy is Brian Marsden. He was the director of the Minor Planet Center. He is the guy to whom you have to report the discovery of all solar system objects. He kept track of all of them. So we reported our discovery to him, and he thought it was interesting, but he was convinced that it was a long period comet. He said, it's just a long period comet on a weird orbit. And he made a bet with us, $500, that it was just a long comet, and it was nothing special. And so quickly he lost. But it took him 4 years to pay. So, and other people told us, well, we were just lucky. He said, basically they said, you're just lucky. There's only one object like this in the whole solar system, and you were lucky. You found it. And we knew this was rubbish because simple statistics says that we look at such a small piece of the sky, and if you found one object in a really small piece of the sky, there must be thousands, millions of these things, right? It's just simple statistics. And but the criticism also didn't bother us, and because we know how to find them now. You find one object, you know you can find more. And 6 months later, we found more objects, and from then on, every single time we went to the telescope, we found more. Basically, you go through a psychological barrier. You know how to find these things, and it became easy. So by now, about 1,500 Kuiper Belt objects have been found by people from all over the world. So if you could look at the Kuiper Belt from outer space, it would look something like this. So this is with all these orbits. So basically, the Kuiper Belt looks kind of donut shaped with so basically a belt. It's kind of thick. It's about 25 to 30 degrees. It extends from about 40 astronomical units to about at least 1,000 astronomical units. The population of the Kuiper Belt, there are about 70,000 objects, larger than 100 kilometers. If you want to count all the way down to 1 kilometer, there's at least 100 million objects. So there's a lot of things in the Kuiper Belt. How much mass does it contain? It's about 1.1 Earth mass, so 10% of the mass of the Earth. Now this is a lot more mass than is in the asteroid belt. So the Kuiper Belt is way more massive than the asteroid belt. But 0.1 Earth mass, that's really not much considering what we see in it. Of course, you've heard about Pluto being in the Kuiper Belt and several other Kuiper Belt objects, 1,000 kilometer size or bigger. In order to form 1,000 kilometer size object, you need a lot more mass than this. This is very little. So from computer simulation, we found that in order to grow things like Pluto in the Kuiper Belt, you need at least about 10 Earth mass, 10, 20 Earth masses. So what that tells you that well, the original Kuiper Belt was much, much more massive than what it is now. So what you have now is about 1% of the original mass. 99% of the mass is gone. And we don't know how, but it's gone. We also know that they collide about 1 kilometer per second. This is pretty fast. So when they collide, they don't stick together anymore. They collide, they break each other up. So things don't grow anymore in the Kuiper Belt because they hit each other with 1 kilometer per second. Okay? So all this tells us that the original Kuiper Belt was much, much more massive than what it is now. Okay. This is probably the most exciting thing that came from the Kuiper Belt. This shows some orbits in the Kuiper Belt. So here's a zoomed up view, if you can look close in. So you can see there are all kinds of orbits. There are little orbits close to the sun, and there are big elliptical orbits very far, extending very far away. So this was really surprising. We had no idea what to expect, what kind of orbits they were on. And then we start finding more, and we calculate orbit, and then we get plots like this, and everybody's just amazed because, well, why are they so different? Why are some orbits so different from the others? This is another way of showing the orbits. And here's just a quick review of ellipses for people who forgot. All orbits in the solar system have the shape of ellipses, like this. And you have the semi-major axis that tells you how big the ellipse is. You have the eccentricity that tells you how elliptical something is. The circle is a special case of an ellipse. It has an eccentricity of 0. So orbits in the solar system are basically all ellipses. Some of them are circular, some are more elliptical. So this plot here is a semi-major axis. It tells you how big the orbit is. The y-axis is eccentricity, tells you how elliptical something is. So if you have a circle, would have an eccentricity of 0. So these are all the Kuiper Belt objects that we have found so far. And you can see, just like in the other plot, they're clustered together. A bunch of them are clumped here, some are lined up here, a bunch are over here. So the orbits are all very different. And they're all, so first I'll just talk about the different types of orbits. First, the red guys, these are called the classical objects. They have nearly circular orbits. They basically form there, they stay there, nothing much happened to them. Okay? The funny thing about them is that they all stop right here. This red line, which is about 50 astronomical units, we call that the Kuiper Belt edge. Why is there an edge? We don't know. People have speculated maybe there was a passing star, but we really don't know why things just stop here. And then there are these objects, the green and the black ones. And these are the big elliptical orbits you saw a bit earlier. This guy. this one, and this one, okay? So these are the big elliptical orbits. Why are they big and elliptical? Well, the green ones, we know. Everything in this arc come close to Neptune. So we know all the green guys, they all come close to Neptune. So continued interaction with Neptune is what gave them these funny orbits. Okay? So we understand why the orbits in green are the way they are, thanks to it because of Neptune. The ones in black, we don't know why. They also have, these orbits are also highly elliptical, they're very big, but they don't come close to Neptune. So we don't know why how they got their orbits. There have been theories, maybe is an unseen planet that nobody has seen that gave them this kind of orbit, maybe there was a passing star, we don't know. Oh, wait, and then the last one, the blue objects, all lined up here. They're located in special areas called the resonances, like here, 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 here. And they're all lined up at these special resonances. And because they're right in resonances, they're called resonant objects. And those locations are special locations. So here's a name, 322 resonance, right, that one. An object in the 322 resonance would make 2 orbits around the sun every time Neptune makes 3 orbits around the sun, okay? An object in the 221 resonance make 1 orbit around the sun every time Neptune makes 2 orbits around the sun. So they have a special relationship with Neptune. Does that make sense? Okay. And because they have this special relationship with Neptune, funny things happen to them. Here. And so resonances happen in our solar system. It also happens in other solar systems. I'm going to show you what happens in a resonance. I'm going to show you a movie. This movie shows the exoplanet system, what is it called? GJ876. It has 2 planets go around it. Here's a star, 2 planets around it. And these planets have 2-to-1 resonance relationship with each other. And I'll show you what happens when you're in a resonance. So what I'm going to show is that, so right now they're all lined up. This guy is going to go twice as fast as this guy. And every time the outer planet comes back to here, they will form a line. And every time it comes back to perihelion, all these things will line up. And it's going to happen over and over again, so you're going to see. Okay? So this guy comes to perihelion, straight line. It comes back to perihelion, straight line. So this guy makes the outer guy with 1 orbit and the inner guy with 2 orbits. So the ratio is 2-to-1. And you can see, so every time the outer planet comes back to here, that straight line reoccurs. So this configuration happens over and over and over again. And that's how the gravitational effects get amplified over and over, because it repeats over and over and over. So all the gravitational effects get amplified because of this repetition of this configuration. Okay? So that's a resonance. So in the Kuiper belt, something similar happens. Same thing with these guys in the resonances. The same configuration happens over and over and over. So that's why they have special, that's why they have special dynamics. This little red P here, this marks Pluto. You can see it completes, so Pluto is a famous inhabitant of the 322 resonance. And you can see it blends in perfectly. If I didn't mark a P there, you would never pick up Pluto. So this argues more than anything why Pluto is not a planet and it's a member of the Kuiper belt object. And being a resonance gives it special properties like it's protected from Neptune, Pluto never collides with Neptune, and the same protection applies to everything else in the resonance. Let's see how much time do I have. I'll briefly mention something called planetary migration. It refers to the fact that the orbits of the planet in the past, they shrank or they expanded. And they did that because of conservation of orbital energy, angular momentum. So the giant planets, Jupiter, Saturn, Uranus, and Neptune, they used to be somewhere else. Then things have changed, and now they're where they used to be. So in the beginning, here's the giant planets. This is the early solar system. So the planets had just formed, but beyond Neptune, there was still a population of icy bodies. Okay? So this was the early solar system. So Neptune, being next to this population of icy things, of course, it scattered everything around. And when it scatters something, there's an exchange of angular momentum, orbit energy. Sometimes, if it scatters something inward, then Neptune stole some energy. If it scatters something outward, then it lost some energy. So all these exchanges of orbital energy resulted in the planets either expanding or shrinking. Okay? So, well, okay, this is all complicated, but all you have to know is that just from scattering all these things around, in the end, Neptune expanded its orbit, same with Uranus and Saturn, but Jupiter is special. Jupiter, its orbit shrank. So, I know it's complicated, but all you have to remember is the giant planets did not used to be where they are now. So here's another picture to show you before and after migration. Before planetary migration, here are the giant planets, and here's Pluto. You can see, you know, they're all on nice circular orbits. And after migration, after the planets have mostly expanded, Neptune moved further out, and Pluto got captured into one of the resonance I showed you earlier. And then the resonance dynamic changed the orbit of Pluto into the current configuration. So, so my point is that the current configuration of the solar system is the result of planetary migration. Okay? So planetary migration, it was, I think somebody first thought of it back in 1984, but nobody paid much attention to the paper because, well, there was no evidence for it. And then the paper came along, and now we really have firm evidence for planetary migration in our solar system and also in other solar systems. Okay, now talk a little bit about the story of Pluto. The story how Pluto came to be a planet is well known. In the early 20th century, people thought that Uranus was moving in a funny way. It was not where it should be. So people thought, oh, there must be a planet perturbing Uranus, and they called this unseen planet Planet X. So people wanted to know where Planet X was. And this guy, Percival Lowell, he built his own observatory to look for Planet X. He hired this guy, Clyde Tombaugh, to look for Planet X. And so Tombaugh started searching, and in 1930, he found Pluto very close to the predicted position, and he said, great, we found Planet X, it's Pluto. But things didn't go very well for Pluto as soon as it was discovered. When Pluto's orbit was determined, it was very clear that it was on a very funny orbit. It was very different from the other planets. Whereas all the other planets are mostly circular, Pluto's orbit is highly elliptical. Whereas the other planet orbits are mostly in a plane, Pluto is highly inclined. It's tilted completely out of the plane. Its orbit even crosses the orbit of Neptune. This is all very strange for something that's supposed to be a planet. And then eventually people found that Pluto was way too small to perturb anything. It's less massive than the moon. It's way less massive than the Earth. It's even smaller than the moon. It's so small that there's no way it could have had any effect on Uranus' position. Later on, people found that this deviation of Uranus was a mistake. It was just an observational error, so there was nothing wrong with the orbit of Uranus. So all the fuss was about nothing. And so we have to conclude that Tombaugh discovered Pluto not because of any prediction, because there was no prediction. He found Pluto just because he was looking and nobody else was. Okay? And then once people were found, people looked back in their photographic plates and they found that Pluto was recorded as early as 1914, way before the real discovery, but it went unnoticed because nobody was looking and nobody cared. And then the story of misdiscovery is really not new. It happens over and over again. Galileo saw Neptune 200 years before Neptune was discovered, but he didn't pay any attention. So Neptune was not discovered until way later on. The Kuiper Belt object that we discovered, the bright ones, were also seen back in the 50s and in the 60s. But again, nobody paid any attention because people were stuck on the idea that Pluto is the last planet. So nobody cared, nobody looked, and then the Kuiper Belt went undiscovered. But in fact, people saw it as early as 1960s. Okay. So it's a story of misdiscovery. Let's see. So after we found the Kuiper Belt, you can imagine that the status of Pluto became shaky. And people start saying that Pluto shouldn't be a planet anymore. And it started a big outcry against Pluto's emotions. There are lots of posters being made like this, and especially this one. I like this one. So people were upset about the idea that Pluto shouldn't be a planet anymore, because they said, well, a lot, you astronomers told us a long time ago that Pluto was a planet, and now you tell us it's not a planet anymore. They felt completely betrayed. They believed us before, why should you believe us now? We keep changing our mind. The answer to that is, it's the nature of science to change. It is our job as scientists to tear down old ideas and replace them with new ideas when the old ones don't fit anymore. Okay? So it's the nature of science to change. You keep looking, you have the data, but if the old theory doesn't fit the data, you have to change. You have to come up with a better theory. That's just the way it is. And it's called scientific progress. Well, many people, as I said, were very upset. And they said that demoting Pluto would be disrespectful to Tombaugh, it would be disrespectful to the public, it would be disrespectful to little kids, because kids really like Pluto. And we don't want to hurt anybody's feelings, especially children's feelings. But science doesn't depend on the public's feeling, it doesn't depend on children's feelings. So all evidence point out that Pluto is much better understood as a Kuiper Belt object. It firmly belongs in the Kuiper Belt, and they really shouldn't have this very misleading name of a planet. So we apologize to little children, but Pluto, which is misclassified as a planet, is basically just another Kuiper Belt object. Okay, so that brings me to the summary. So we started our survey of the solar system, not because we were looking for the Kuiper Belt, but because we had a question. Why was the outer solar system so empty? And that was a question that drove us, and that's what we set out to answer. And then we found the Kuiper Belt. And since the discovery, it has basically completely changed our understanding of the solar system. We used to think that we knew everything in the old solar system. We used to think that the planets was on fixed stationary orbits. They were just there forever. Things and nothing was to change. And now we found that lots of things were going on. The planets move in, they move out. And beyond Neptune, there's this big population of things called the Kuiper Belt. And it revealed all kinds of things that we never suspected. It has funny orbits that we don't understand. So basically, we went from something that we thought we understood very well to something that we don't understand at all, kind of. So is that progress? Is that depressing? Well, I don't think so. I think it's progress, because if nothing else, it means that many more discoveries are waiting to be made in our solar system. And that's it.
So now I have a question for you. Actually, first of all, does anybody have any questions for Dr. Liu?
Is it possible that the asteroid belt was caused by Jupiter's inward? That it did something, or it was moving them?
It certainly, it had, Jupiter didn't move much. The other, it's so massive that even though it had to shrink, the orbit had to shrink a little bit, but it only shrank a very, very small amount. It's so massive, it's just hard to move Jupiter. So Jupiter's presence, of course, has some effect on the asteroid belt, but its motion in, the shrinking of Jupiter orbit, I don't think that did much, okay, because it didn't move much.
I don't have much of a background in astronomy, but you know, with Pluto, there seem to be more exceptions. Why do people think it was a planet in the first place?
It's PR. It's propaganda. So because they thought that there must have been a planet X, so people went looking for it, and they found Pluto, and they said, that's it, that's our planet. And it's cool to say that you found a planet. So it's just propaganda. Yes?
Do you believe that there are things like more planets beyond the Pluto that are affected by the sun's gravitational pull?
Of course, everything in the solar system revolves around the sun. It's within the sun's gravitational pull. That's the definition of the solar system. Everything in the solar system orbits around the sun. If it doesn't orbit around the sun, then it's not in the solar system.
What about other planets?
They orbit around their own stars. Like I show you that picture there, you see lots and lots of stars, and it turns out that most stars have planets, and those planets go around their own stars. So that's their own little solar system.
Don't forget the sun is a star.
Yeah.
On the second question that you have, when planets come in very form,
Yeah.
I always thought that I was told that the heavy material
well, that goes back to cosmology. In the beginning, there was only hydrogen and then helium, and then from then, stars made heavier materials.
The question is whether we know anything about where they actually did come from.
Sure, because we understand stellar theory quite well. We understand where elements come from. In the beginning, in the primordial universe, there was only hydrogen and helium, but then stars were formed, and that's how you made heavier things. All the heavier elements and hydrogen and helium were made inside stars, and then they got dispersed throughout the entire universe.
Any other questions?
Those heavy material are not coming from our sun, which they call August.
That's right, because where did the sun come from, right? So,
Yeah. Yes, sir.
So, what makes the planet's orbit in a plane but not in a 3D form?
okay, I'll show you that. Okay, the reason is angular momentum. Where is it? This one. Yeah. So here's the question is, why does it form a flat disk and not? Because originally it was a big molecular cloud, this big spherical cloud. It collapsed because it was too massive, it was too heavy. So it collapsed onto itself. And it collapsed into a little small ball, but it spins, right? Remember, you take this. If you spin, if you get something spinning, and something smaller spins faster than something that's extended. So it spins, and then it makes a disk because of centrifugal force.
But in this picture, you say that the planets are formed from helium and gas, right? So the Kuiper object, basically they collide with each other all the time. Why don't they form bigger and bigger objects? But you say that they collide and disappear.
They hit each other at the speed of 1 kilometer per second.
Yes.
And that's a high velocity collision. So when you put two things together and they collide 1 kilometer per second, they're not going to stick.
So the Kuiper object will never.
And now, but in the original, back in this stage, the collision was more gentle. If they were not gentle, nothing would form, right? So in the early solar system, the collision were much more gentle. So that's how things stick and they grow bigger and bigger. Right now, at this stage in the Kuiper belt, they collide at high velocity, so that they're not sticking anymore.
That's why we're not supposed to drive too fast.
Is there any connection between that missing mass of the Kuiper belt and the Oort cloud, maybe?
Yeah, we think that the Oort cloud. I show you that picture where there used to be a disk beyond Neptune and things got scattered away. Some fraction of it got into the Oort cloud.
What about the idea that everything in the universe is just a smaller amount of other things in the universe? Like the solar system, is it similar to an electron cloud configuration, like how the planets have their own gravitational pull and they can pull other things, and like sun could theoretically be similar to a nucleus of an atom?
That's an analogy, but it has to just do, yeah, so you're talking about the atom has electrons all going around the nucleus. It's kind of similar to this, I suppose, but I wouldn't draw the analogy because gravity doesn't work very well at the quantum level, so it's not gravity that drives everything. But for the sun and the planet, it's gravity. That's the only thing there is, gravity that makes everything go round.
And you might want to explore that when you go to college. Any other questions?
What prevents Neptune from absorbing all the Kuiper object?
Why? Well, it's cleared everything out. It scattered everything away mostly. So what is left is on orbits that are fairly stable, or if they come close enough at this time, they get scattered again. So yeah, things it doesn't absorb anything anymore because things collide at high velocity. Okay. Somebody had a question back there.
Yeah, aside from science, can you tell us a little more about life, astronomy, how much time you spend in the lab?
Okay. Life as an astronomer. I show you some pictures of a lot of nights sitting at the telescope. It's pretty miserable. Where is it? Yeah, okay. So, well, life in the, so if I was an observer, so I use a telescope. So you have to ask for telescope time. And it's hard getting telescope time because everybody else wants telescope time. So you write a proposal. You write a proposal and you say, please give me 3 nights on this telescope so I can observe whatever. And if you're lucky, you get the telescope time, then you go to the telescope. And the telescope is usually on top of a mountain in the middle of nowhere. So you do a lot of driving. And then you go sit in the control room during the night. So the control room looks like this. There are computers. And the telescope is controlled by computers. You don't have to stand behind the telescope and look at it anymore. So you do everything with the computer. You control your camera, CCD camera with the computer. You control the telescope with your computer. And you just sit there and you work all night. So let's see. You eat dinner at around 4:30 in the afternoon. And then about 5:30, you drive to the telescope to get ready to wait for sunset. Then the sunset, then you start working. So that's about 6, it depends the time of the year. So you start working around 6 p.m. or so. So you sit in a room like this all night long. You get tired, you get sleepy, you get hungry, you get cold, and then if the weather's good, you work until sunrise, so at 6 a.m. So you work about 12 hours. And then you drive down the mountain and you sleep during the day, and you hope nobody wakes you up. And sometimes it's cloudy and it's bad weather like that, and you sit there and you wait all night long, or you take naps. And then you have the data, and then you go home. You're really happy to leave the mountain so you can go home and have a normal life again. And then you analyze your data in your office with your computer, and you say, oh, I found something. This looks interesting. I should go back and check on it. And you write another telescope proposal, and you go back, and you do the whole thing all over again.
Yes, sir.
So it's not that exciting. So what kind of job?
It's exciting when you find things that nobody's ever seen before. That's exciting. And then you completely change our understanding of the solar system. That's pretty exciting. But not everybody's that lucky. Lots of times you just work and you find that you don't make discoveries all the time. Sometimes you make small discoveries that people, that doesn't make it to the front page of the New York Times. But you're just pushing the edge of science a little bit. Most of the time, it's little bit. Once in a while, you let lucky, and then you push the edge of science by a lot. But that's rare. So most of the time, you're just making little discoveries.
Yes, ma'am.
The picture that shows the women looking at the slides is
Yes.
so primitive.
Yes.
But with the new technologies coming out, do you anticipate more discoveries, more rewriting of theories?
Sure, discoveries always change science, and that's how science progresses. And astronomy it's a science that's completely driven by technology. You get better detectors, you make better observations. When we used a large CCD for the first time, we made the discovery right away. It's completely driven by technology. You have the best instruments in the world, you make the best observations in the world. That's all it is. It's completely technology driven.
Wow, more questions. Go ahead.
What do you think about the prospect of the new planet, Gaia, that was discovered around 4 years ago?
Oh, okay. Oh, so exoplanets, they're found all the time now. People are excited about them because they're in a region they call them Earth-like planets. So maybe there's life on it, and that's what people are excited about. And there will be more and more found, and I think it's exciting. And so the question is, when and how are you going to detect signs of life? So right now you find these planets in the right location where there should be life, but so the question is, can you find life? I don't know. Ern.
If you had to talk to those budding scientists here in the room to give them maybe just 3 pieces of advice, what would it be?
Okay, the first one is work hard. You also need luck, but you have to work hard. That's you can't get around that. Second one is find something you like. If you like something, you're going to work hard at it, so you'll be good at it without trying. Because if you like it, you're going to work hard at it. Third one, if if you have a question that you really want to answer, you should stick to it, even when other people tell you that you're crazy, you're stupid, you're wasting time.
Thank you.
The community of radio astronomers would probably is pretty small.
Yeah.
And I guess that you probably know most of them, or
Yes.
majority of them. Do you have any observation on how advanced or how much progress the emerging countries in Asia are making in terms of radio astronomy?
At this moment, I don't see that much. Astronomy is still a luxury of countries that are well off. So I haven't seen, I haven't met many astronomers from emerging countries. The country had to reach a certain level of prosperity before it can put money into astronomy.
Yes, sir.
The telescope that you showed there basically stationary, so astronomers need to look into the sky to
Yeah.
discover something. So we have all the telescopes like Hubble and things like that on outer space. I guess at the time there is very precious.
Yes, right.
Is there any idea that to deal a synchronized orbit of telescope that you can always look into the sky and
Space telescope, synchronized space telescope. I think people talk about it.
very expensive?
The idea is to put them on small satellites. Send small satellites up and somehow open them up. So that's the idea. Send up a bunch of small satellites, not like this big, and they'll be cheap. Send up a lot of them, and somehow they would each have a mirror that opens up. So that's the idea.
Section of the sky.
Exactly. Yeah. So people are talking about that.
Talking about it.
Yeah, but people are trying. They are building small satellites instead of spending a lot of money, $1 billion on a big satellite. Send a small satellite, cost them less than $1 million to build and send up. So that's where the technology is trying to go.
Any other questions? All right, so now I'm going to turn it around and ask you questions, and especially if you're under 18, like I promised you, you'll get a little prize. But in the meantime, I need a helper. So, Amy, can you come up here and help me, please? Amy is one of our instructors also under a program sponsored by APACAF. It's SATs on Saturday, and she and Taidak help with that program. She's one of our English teachers who help students write very good essays. Anybody here like writing? Amy is a very good writer, okay? And if you ever need help with writing, you can ask Amy. So we have gifts in these boxes and bags. We have gifts for boys and girls can play with boys' toys too, okay? But you want to take a few gifts out and show them what they would get if they if they answered a question correctly. So for girls, if you like Lego Friends, we have Lego Friends. If you're a boy and a girl, and you like this Chub City iPlay interactive figure, we've got lots of that to give away as well, okay? So now, first question for you. Dr. Liu said that when she had to observe, where did she go? Do you remember? Anybody know? Yes, sir. Hawaii. She went to Hawaii, correct. Would you like the Lego Friends or the little Chub City guy? I like her friends. There you go. All right. And in addition to Hawaii, she went somewhere in Hawaii to actually do the observation. Yes, ma'am.
Mauna Kea.
Yes, ma'am. She what?
Mauna Kea. She said it right.
Mauna Kea, yes.
That's right.
And then she was in this specific building. And what kind of building is that called? Yes, sir.
An observatory.
Observatory, correct. All right. Come on, Amy. I need your help, Amy. More gifts. The gentleman right there, he deserves a gift. You want to come up and get your gift? All right, so she was in Hawaii, Mauna Kea, in an observatory, right? In the observatory, she said that It was very hard to do what? Because of the gravity. What?
Because it was high up in the mountains where it's really high and hard to breathe.
And so was she alert all the time or feel
Very
very good?
You should ask, what's Pluto?
All right, so now, what is Pluto? Yes, ma'am. It's a planet?
Oh, no! No!
Is Pluto a planet? It was a planet. She insists that it has to be a planet. I'm sorry.
No.
Yes, sir. It's a dwarf.
Okay, all right.
Is that,
I never said dwarf planet.
she didn't say, no, she didn't say dwarf planet. No. This is a tricky question. Very tricky.
No.
A curvature thing she forgot. Curvature
Here, look.
object. Think about that. Yes, ma'am. It's a member of the Kuiper belt.
Yeah,
Yes. Very good. Good memory. All right. There's more questions. Don't worry. Don't worry. All right. What is our sun also considered to be? If you already answered a question and got a prize, you can't answer again. Yes, ma'am. It's a star. Correct. You guys are better than me in science than I was when I was your age. All right. Now, thinking back, okay? This is a little bit hard, all right? When planets are formed, okay, do they go at a very high speed and collide or a little bit slower? Yes, ma'am. A little bit slower, right?
Right.
There you go. Good job. You guys are way too smart. I'm running out of questions. Is there any other questions you want me to ask them?
How do you find a solar system body in your images?
How did you find solar system body? What did she use? What tools, methods did she use? If you answered the question already and got it correctly, don't raise your hand. Yes, sir. CCD. Yes.
So how do you recognize a solar system body from a star or a galaxy?
Ooh, that's a hard question. Parents, help out. It's moving?
That's right. That's right. If it moves, that's right.
Okay, so when you're trying to observe, do you just do it overnight one time, or do you have to do it over a long period of time? Yes, ma'am. A long period of time. Very good. Okay, so the other question, and this might be a little bit easier question. The planets, what did they do around the sun? They rotate around the sun. And here's a follow-up question, okay? But you get your prize now. I'm going to ask a follow-up question to that. You can get one of your prize now. The follow-up question is, okay, the planets that are on the outside, do they go faster or slower than the planets in the inside, closer to the sun? You already got the question. You already got a prize. Anybody who hasn't have a prize yet, you're under 18, you want a prize? Yes, sir. Oh. Slower, correct. Right. Very good. Now, here's a question that only one student can answer in this room, okay? Who is the youngest child here? Who's the youngest child here?
Probably him. It's a baby.
Anybody? How old are you, young man? 5. Anybody else here younger than 5? You get a prize. Come on up. Thank you for being a very patient listener. And I'm afraid to ask this question. Who's the oldest person here?
Nobody's going to admit.
There might be somebody. About 60. Is there anybody over 60? I'm pretty sure there is. Somebody doesn't want to admit it, though. All right, there is probably somebody over, but you do also get a prize for being a very good listener today, too. Did you like it? All right, any other student here who did not get a prize yet? Raise your hand. I have a very easy question for you. Name one thing that you learned today. You want to say it louder? She learned about planets, Amy. Gotta give her a prize. Anybody else have not gotten their prize yet? Anybody else? Did you get a prize yet? Oh, you did. Oh, if you haven't got a prize yet and you would like one, you're under 18, let me know. I want you to also answer the question, what did you learn today? You've already got it one, sir. No. Can't get more than one. All right. Well, we thank you for being here today, and we hope that you had a fun time and enjoyed something. Thank you, Dr. Liu, for traveling from Boston. And on your way out, if you'd like any refreshments, snacks, please feel free to get some. Thank you. Thank you, Amy. You're welcome.
That was fun.
Thank you so much.
Thank you for it.
Make it fun and learn it. How are you?
Of course. Just call me Jane. Don't call me Dr. Liu.